Hi everyone, this is Emma. Today I'm going to give everyone a brief intro into computer vision, and hopefully this is going to be helpful for everyone in the program. Cool, and first of all, this is the agenda I'm going to cover today, and if you're already familiar with computer vision, feel free to skip one or several of the sections here. But I do recommend maybe going over this video a little bit more and maybe check out some of the references at the very end, because a lot of the discussion are really interesting. And also, I think I'm going to provide a little bit more ideas about how we can use computer vision in this course and why we want to give a really short intro at the very beginning of the course. Cool. So I think computer vision is a very popular area as of today. And I'm pretty sure everyone is also really familiar with the concept of vision. But it's really interesting. While I was preparing for this course, I found a very interesting quote that this is from one of the really famous professors in the computer vision area, Fei Li. And her quote is just like, to hear is not the same as to listen, to take pictures is not the same as to see. And I think she's trying to strengthen and with today's technology, it is super easy to have video camera, to have super high resolution cameras where you can just record and save every moment. However, it is a very different story to, it is a very different thing to take a photo or save a photo somewhere than to actually be able to understand what is the content in the photo or try to infer what is happening behind the scene. So I think this is the idea as to, in this highly digitized world, how can we best use the power of computers to understand how we're going to perceive the world. So just want to go over some really quick, simple concepts here, like visual conception is one of the most important senses humans have. And it is simply the act of observing patterns and objects through the sight or visual input. And our visual system allows us to build a model of the physical world that is basically saying human beings, and also a lot of other animals as well, use the visual input to perceive the world around them, and also to build understanding and also to build understanding about the physical world around. And also, like, if you're familiar with the AI system, you can see it also requires two key components. First of all is to understand the environment around it. And second, based on the environment and the current situation, the AI is going to take actions based on the perception. And also usually we're trying to optimize some kind of objective function. And this is a very important part, as you can see the first point here is just perceive and understand the environment around. So this is where computer vision is actually super important. It could be the bridge or the eye with the computer and the external world, where we are going to use sensors, images, algorithm to perceive and construct, maybe in computers understanding, a physical model of the world so that the AI system can take the appropriate action. So that being said, the bullet one here is the absolute foundation of bullet two. Take a very simple example here. Maybe you want to build an AI that can maybe you want to build an algorithm or AI that can drive a car, but it's really hard to imagine the AI or the car doesn't know the surrounding, which is the road conditions, the weather, the lighting, everything, without taking the appropriate action, such as, should I accelerate, should I stop, should I make a turn? So the computer vision and also a lot of other sensors, signals to build understanding of our surrounding is absolutely important foundation for a lot of problems the AI is trying to solve. And also, as you can imagine, while I was giving a lot of introduction as to vision and sensor, you can imagine computer vision is actually very interdisciplinary. Um, that said, it actually touches on many, many fields of science and technology. As you can imagine, like the word vision implies it is biologically or is trying to mimic how animals and human trying to perceive the world, how the animals can see through our eyes. And so this is where you can see some kind of connection in biology and physiology, where you can neuroscience and cognitive science tie very nicely to computer vision. And on the physics side, you have the optics, image processing. These will actually build the backbones to images, videos, understanding all the signals in the digital world, and then how we're going to almost like translate all the signals in the physical world into the world, the signals computer can understand. And also in engineering, this is also very tightly connected, but also sometimes this is a combination of a more complex problem. For example, we'll see sometimes vision or video image tied together with speech and language processing. And also you'll see these signals being processed and translate to some kind of different commands or the actions AI going to take, and those will be the command for the robots or robotics to execute. And so, and also of course, machine learning and information retrieval, also these are built on top of the mathematics, statistics, and engineering pieces of the computer science world. Yeah, basically everything listed here, you can easily imagine an example where some of these disciplines and fields are being heavily leveraged by computer vision. So it requires a pretty broad understanding of a lot of the different contexts here. You do not need to know everything here to learn about computer vision, but I think this is a really fascinating discipline that can be connected to everything around us. And going to our next slide, just want to give some like super brief intro or about the history of computer vision, because I think today we live in such an exciting environment with the advancement of technology that whenever we're thinking about computer vision, we're thinking about deep learning, convolutional neural network, and super, super fancy, huge models with millions, billions of hyperparameters, or thinking about self-driving cars and like really amazing filters that can be applied real time. But you can imagine like every super advanced technology has to start from somewhere. And there is a link I link at the very bottom of the slide, and it has covered some really interesting history that they dated back to, I think, the 1960s or 1970s, where the computer vision field was first created. And basically it started with really simple techniques for image processing with filters, or you can call kernels, basically different matrix calculation to detect edges in the image. Is like super simple if that comparing that with what we're doing today with convolutional neural nets. But it is actually a really good starting point. And then you're seeing interesting image transformation technologies that can actually map 2D images to 3D, where it's also allowing some kind of 3D reconstruction of objects. And I think next, this is actually still really popular techniques that's being used in everyday life, which is the optical character recognition, or it's called OCR. You can see this in everything. For example, if you use any kind of the banking apps on your phone, at least for me, I haven't been to a bank to deposit a check in a few years, because a lot of the banking apps now offer just depositing a check by taking a couple of photos on your phone, and that's done. And also a lot of the digitization of paper documents, you're also using OCR. Basically, it's a really, really straightforward algorithm that can convert a photo or an image of text into letters or words, basically transform your image into the entire digitized document, which is super handy and super helpful. And later, I think in the 1990s, where machine learning and statistical models are taking off, you can see the fast growth of computer vision as well. There are multiple pattern recognition algorithms, and combined with image processing, where you can extract different features. And also, that's when we have really simple or the basic neural nets. And when you're stacking the pieces together, you have the booming pattern recognition of images. A very interesting example, or like I'm pretty sure everyone is really familiar with this example, is when we have the facial recognition on the cameras. It is actually really, really amazing invention at that time, considering the computer chips are not as fast as they are today. And a lot of the cameras can actually incorporate facial detection real time when you're taking the photo. So this is definitely one of the bigger steps. And since the 2000s, there has been a lot of research in deep learning, or well, it starts with maybe the neural networks and then turn into multiple layers, which is deep learning. And also there are a lot of evolution in the structure of neural networks, like recurrent neural networks and convolution neural networks. And this is a booming new era of computer vision, as you can imagine, with the growth of computation power, and also the architecture of neural nets are getting more and more complex. And this is when CV really starts to shine. And with the cost of computation and hardware become cheaper and cheaper, we're seeing more use of computer vision almost everywhere. I'll show some really simple application in one of the future slides. And before jumping into examples, I kind of want to give you a really brief intro about different types of computer vision tasks. I want to quickly cover several types of computer vision tasks, so that when we are going to review some of the application examples of computer vision, I really want you to maybe pause for a few seconds and think about what are the key components that's being leveraged in the application, and what are some of the problems or the smaller pieces of the tasks being leveraged. I think maybe I can give you one example in one of the applications, and I'd really like to discuss this if we are having this class live. But feel free to leave comments in our GitHub repo, or send email or comments, or in any way of communication if you have any question or comments. Cool, maybe let's jump into the first slide of different types of computer vision tasks. Well, here we have some cute cats and dogs, which are adorable. These are definitely really interesting photos, and to humans, this is really easy to understand and process. On the left-hand side, there are two photos with just a single object, which is a cat. And you can see there's only one object of interest here. Well, theoretically or technically, the grass in the background is also can be classified as something we want to look at. But usually we will focus on the cat here first. And you can see in the first example here, we're basically trying to do some object classification. And this is basically to answer the question, what is the category of the object that is in this photograph? And this is a very generalized question, as we basically have this entire image, and this problem is narrowed down as to we want to classify this image into one object. This is to, as we'll see in later examples, this is a very simple and really straightforward problem to solve. However, this usually means you will need to do a lot of pre-processing. As you can imagine, in the real world images, you will, well, sometimes you'll see really nice and clean photos like this, but usually you will more likely than not, you'll see a photo with a lot of background on other people, other objects in the photo that may or may not be of interest. And if you really want to do a really good job as classification, you will need to basically get rid of all the noises, all the signal that's not helpful, and try to let the algorithm to focus on the most important piece. So yeah, this is what we want to discuss first. Also most straightforward, the object classification. And the second example here, second on the left, is classification plus localization. This is slightly more challenging than the first task, as what is as well need we also in addition to knowing what is the category of the object, you also need to localize it, which is to identify the location of this object, as indicated here in the red box. This could be done in different ways, but usually this means you will need to have some kind of understanding about the broader sense of what is in the photo. And this will be super helpful in a lot of the other tasks. For example, like if you want to do video tagging, or if you want to do some kind of tracking of moving objects, this will be super helpful to understand this first. And the third example here is object detection. And this is basically, as you can imagine, things are getting a little bit more complex as the third and fourth photos have multiple objects. You have a cat, a dog, and a rubber duck, which is classified as a duck here. But the key here is I want to know how many objects there are in the photo, and I want to know where they are. And then I also need to know what is the object I'm trying to look for. Then I can answer the question of object detection, which is where are the objects of interest in this photo? For example, in this example, we can answer the question like, where is the rubber duck? This is basically, you need to know, first of all, if there is a duck, and second, we'll have the localization of the duck. The answer could be like, there is no duck in this photo, which is, of course, acceptable answer to this as well. And the fourth here is instance segmentation. I think this is also pretty interesting, as you might see techniques of this from maybe some of the photo editing apps or other really interesting application about filters or switching up backgrounds, or maybe when you're using Zoom, you want to replace your background with a virtual background or blur out the surrounding. This is also just trying to get a sense of the object as well as the edge of the object. So this requires maybe a slightly little bit more accuracy in how this algorithm is working. So I think this covers, and we're really trying to compare and contrast what are some of the key tasks we can achieve with computer vision. But also there are a lot of the other things we can achieve. For example, I think there's no example here of being on the slide, but sometimes you want to have like a scene segmentation, which is very, very, very similar to the last example of instance segmentation. But as you can imagine, like, well, it's more about the background, foreground, what is the object of interest here? Like, we can be separating the scene from the photo, and we can also do some kind of interpretation about the background of the photo. And also, I'm pretty sure a lot of you play with different types of filters that can change your photo into different styles. And so it was a really famous paper, and I believe it was released into a phone app. Is basically you can apply different styles of filters trained on different famous painting styles. You can convert a photo you just take on your phone to a painting of Van Gogh, and there are a lot of interesting applications of that filter. So that is also something based on computer vision, like you'll need to learn from the visual representation of different paintings and also apply those into new images. Cool, so we were just discussing several use cases of computer vision in the images. And now I want to switch gear and think about on a higher level, like videos are basically frames of images stacked together. And of course, whatever technique we're applying to images can be easily applied to video with some modification. As the image here is showing, you have the car, you have different people, and you have them localized in different boxes, frame by frame. So you can do a lot of different things here, like you can do motion analysis, where you can use computer vision to estimate maybe how fast the car is going. And you can do this by estimating maybe the distance between your point of view and the object. You can anchor it to different comparison object in the video. And also you can do image segmentation, where you can use algorithm to partition images into multiple sets of views. And also you can do, sometimes you can do scene reconstruction. I think if you have videos taken from different angles of the same scene, theoretically you can have the complete information about the physical world from different angles, and you can use all of those information to reconstruct a 3D model of the real physical world, which give you a which give you a paranumeric view. Oh, never mind. It's a 360 view of what is actually happening in the physical world. I think that's a super cool technique. And sometimes you can see that in movies or in some of the TV shows. And those are basically built on top of computer vision techniques that merge different camera footages into a 3D model. Cool. And also another really cool application of computer vision will be content-based image retrieval. This sounds really high level. However, I'm sure like maybe all of you have used something similar to this, which is you give an image to an algorithm or give it to a website and try to search for images that are similar to this. And I also know there are a lot of online shopping websites that now allow you to upload the image you're looking for, and then it's going to return a lot of items based on the image you upload. And this is just based on this is basically the content-based image retrieval. And you can imagine a lot of different use cases of this, like Google search, and I mentioned retail, and also you can build recommenders based on a lot of because the query here could be super broad. It could be something the user submitted as a query. It could be, for example, my browsing history, or maybe on YouTube, what I have watched. And theoretically, these are all images or queries like the algorithm can extract really important information from, and then it can return an answer. And then basically you can use it for recommendation, use it for targeting, a lot of other use cases. And I think this is a really, really advanced field, even though it is less shiny or most people just take it for granted, as compared to maybe something a little bit more fancier like self-driving car. But this is also very, very important piece of the computer vision world. Cool. And as I promised, we're now going to go over some of the applications. Do keep in mind, like we quickly cover some of the high-level computer vision tasks. I'm not being super exhaustive here, but just want to give you some basic ideas and concepts about what computer vision can achieve, because we are going to give a more thorough review of the course later in this semester or in this cohort. But just want to really quickly go over some examples. I am personally really familiar with all of these, the reason why I put them here. But I think these are also like pretty common to the broader group now. First of all, facial recognition, as I mentioned, like in cameras and maybe on your phone, like I put the Face ID here, you're using this almost on a daily basis. And this is, we're using this for identity recognition, We're using this for security checks. We're also sometimes just using it for fun, like tagging folks on your Facebook posts, or sometimes you can use it for super serious issue, like trying to identify criminals in the CCTV footage. All of these are pretty widely used facial recognition techniques. And second example here is medical image analysis and diagnostics. This is a really, really meaningful field. As you can imagine, a lot of the medical imaging results, like if you got a CT or some kind of PET scan, there are patterns for certain diseases or really early stage signals in those images. And human eyes can sometimes do a really good job identifying anomalies or identify really early stage signals. But I think there has been papers reporting sometimes computer algorithm can actually do a better job if you train them with labeled training set. So I think this is actually a really exciting application that's going to save a lot of time of doctors. Like you can use a computer vision algorithm to do a really preliminary screening of the image results, and then that can actually save a lot of specialist time because they only need to maybe verify or double check a lot of the results the computer is generating. Third example, super hot area now, and I think everyone's maybe familiar with the concept, is self-driving cars. Of course, there are different types of techniques being used. Some of them are using just video purely based on video understanding and computer vision. Others are using maybe LiDAR and other sensors as well. But I'm just showing here, like in the video or in the photo of this self-driving car, there are a lot of different techniques, as we mentioned. You have the localization of objects, recognition of objects, like is this a car? Is there a person walking in front of my car? There is video analysis, like how fast am I growing? Am I going compared to my surroundings, and trying to project the route while the car is going. Tons and tons of tasks that actually requires algorithm to make a decision on the fly. So as this is a really hot area that require a lot of computer vision expertise. And fourth example here, automation of human tasks. I'm listing here as like Amazon Go. This is a really interesting grocery, basically cashier free or checkout free grocery stores where you can just go in, grab something, and just quickly run out without ever need to tell the cashier what you brought and pay for it. Because with AI, computer vision, machine learning, the camera and the sensors plus the algorithm can figure out what exactly did you buy or did you pick up, and then charge you to your account. And this is pretty exciting, especially considering they can do it with a really high accuracy. But also just want to mention there are a lot of other automation of human tasks with the help of computer vision. For example, in the warehouses, the robots are helping to pick different items from the shelves and pack a lot of the things. And also I think I've seen sometimes in the restaurants, you have this deliver bot, just deliver drinks and dishes to your table. As you can imagine, you can also break down a lot of the smaller tasks the robot is doing to achieve this goal. And fifth here is video and image caption. This is very meaningful in terms of, first of all, like we are going to actually use this technique to understand the world, understand the digital content. For example, now you can just maybe feed the videos through this algorithm and generate content about what the image is about and how, like, as to what objects in there, what is their relationship. And for videos, you can maybe quickly understand what is in the video, or what is the topic, what is main characters without actually watching it. So that's actually pretty powerful, and you can use those information for some recommendation, classification, hierarchical clustering, whatever downstream tasks you want to perform. But also this is super meaningful in the second, like at least to me, as to we'll cover this later. but whatever algorithm or like really complex convolution neural nets we're using now require training. Most of the time, the training will require labeled data. And this process of labeling images and videos is, as you can imagine, very labor intensive. And so this could be the bottleneck for a lot of the trainings for the future, as we may rely on human power to label images for the algorithm to grow a little bit more smarter. However, like if you can achieve like relatively accurate image and video caption, so we can actually teach the computer to do this, and then it will generate a little bit more samples, more training samples to make the algorithm even smarter. So this is, in my opinion, a very important step in the process. And one last example I'm going to mention here is emotion or sentiment recognition. This is technically part of the facial recognition here, but I kind of want to put it separately as a topic here, as this is more connected to, I would say, something a little bit more subtle about human, as emotion or sentiment, usually there's no ground truth, or it is very, very hard to connect it with anything, I would say, in the physical world, unless you ask this person or you have a little bit more context about what exactly means from this image or video. It's going to be super challenging. And also, this is also something a little bit more connected to the human being, to the psychological world, and also could be leveraged for a lot of meaningful tasks. Just imagine for now, like you're using Siri, you're using Alexa, you're using your phone for a lot of the like mundane tasks. How imagine in the future, like when you're unlocking your screen with your face, Siri can also understand like, hey, you're actually not feeling great now. You look a little bit depressed, and here is some songs, or here's like some funny cat video that can boost your emotion or something. Or there could be like real application, as you can detect distress signals on people's faces, or you can detect some more sophisticated sentiment that can be combined with the environment and with other signals to boost the accuracy in other tasks. So I think these are also pretty interesting. Cool. I think we touched upon a lot of the, I would say, like broader topics about what is computer vision and what it can achieve. So I just want to maybe give a really, really simple, like almost like a toy example of computer vision pipeline, so that we can have a better understanding about the end-to-end process about how to train or how to build a computer vision solution. And I'll explain why, like I said, build or train, since like, yeah, in other models, it may not necessarily have a lot of distinction, but here, well, I'll explain why. As you can see, there are 5 different boxes, starting with input data and pre-processing, selecting areas of interest, and then feature extraction. And actually, all of these, we can do like the first 4 tasks with or without any kind of like machine learning, or I would say AI. Like you can do, sometimes you can boost certain signals, or you can use some really fancy algorithms to improve certain steps here. But like I would say, theoretically can do all of these without like a really fancy algorithm. And all of these could be like aggregated into pre-processing or generating the data for the final model. And then in the purple box, you have prediction or recognition. I think this is maybe an overgeneralization of this, like because in most use cases, you will need to train a model based on the feature extracted, and have like of course in the data, like you're training a model, have your input features as well as the output label or the target or interest in training. And after training the model and tuning the hyperparameters, you will end up with a model. And then you can score additional images for prediction or recognition based on the use case. And then the last step will be take actions based on the computer vision model results. Let's take a really quick example here. This is based on the computer vision or deep learning nanodegree on Udacity, and I'm borrowing their really nice flowchart here. Here you're seeing this is a photo of the instructor, and she's just taking a photo. And our goal here is trying to analyze or classify the facial expression on her face. We start with the input data on the very left-hand side. We have this is a raw image, I think taken maybe on the phone. And so you have the image here, maybe cropped it to the appropriate size, because image is basically the array of pixels. And I'll quickly cover on the next slide how the computer, this is how human view the photo, but also in the eye of the computer or in the brain of computers, you'll see the image in a very different way. But the input data usually will do cropping and some kind of like, if it's a video, we will take different frames of image from the video. The second step will be pre-processing. As you can see here, you're seeing the colors being slightly different. And sometimes there will be color correction. And then you'll see the image also scale differently, because sometimes we want the training data to have the same size, so that the task is a little bit more standardized. And also sometimes you also have noise reduction. This is also trying to make sure the information is pre-processed and standardized for the algorithm that's happening next. And third step here is selecting area of interest. And since we are trying to classify the facial expression, it's very important that we first detect if there is a face in the image. And once we detect the face, we can localize or like try to crop and identify the exact location of the face here so that we can put everything into perspective. And the next step will be feature extraction. And I think here the model is probably already pre-built. As you can see here, the key step is to find the facial markers like your mouth, your eyes, your nose, and other things that could be changing with your facial expression. So here actually there, like say we build a model using these facial markers, and so but also we could also be building this model using just like a pretty simple or really I would say naive or brute force solution, like we'll just look at the entire face. I think there are just different ways you can set up your model, but this is maybe one of the smarter ways, like only looking at the features that matters most to reduce training computation. And then the last step here, as I mentioned, the model is probably pre-trained, and you have the final step of prediction. You're feeding all of the facial marker values or like these features into the model. Then based on the eye, the mouth position in this image, and the model is going to make a prediction as to what are the possible outcomes based on the information. And usually these models will be a probabilistic model. And then, for example, this predicts 90% relaxed and 98% joy. And depends on your use case. Sometimes you want to do a softmax and only output the single category that you have the highest confidence. But other times you want to have maybe a global threshold. You can output like multiple categories based on your use case. And as I promised, here's an example of data preprocessing. I'm linking here, like there's a link down below, which explains what's being plotted here. This is a simple illustration of the grayscale image on the left. So this is an image of Abraham Lincoln, and then each of the small boxes represents a pixel, and a pixel is a single 8-bit number that ranges from 0 to 155. Oh, sorry, 255. 0 means it's a black pixel, and then 255 meaning it's a white pixel, and then in all the other integers in between are different shades of gray, and this is why this is called a grayscale representation. And then you can see on the left-hand side, that's the raw image, and in the middle is the pixel overlaid with the numbers, and then on the right-hand side, that is actually the matrix representation of the image. As you can see, this is basically just a number of matrix. And also, like, sometimes you'll have maybe this 2D representation of the matrices. Sometimes you'll have maybe just a flattened 1D array of all the numbers, given that you set a rule of how the matrix can be flattened into a vector. And so this is an example of grayscale. And then in the world of the colors with RGB, I think this is a really standardized way of representing color, even though you have different color representation system as well. This is the most widely used. RGB stands for red, green, and blue. And each of these elementary or primary colors also range from 0 to 255. And then by mixing the 3 colors and your black and white, you will get the colorful world we're seeing with our human eyes. And here is an example of feature extraction. As I mentioned, like, the feature extraction could be super straightforward, or it could be actually pretty complicated. I'm showing here as something that is maybe in between. It is not the most simple method, but also it's not as complex as a lot of the CNN are doing nowadays. I think what this method is doing is trying to divide the image into smaller cells and then calculate the local intensity histogram, which 8 bins for each of these cells as a local feature. So this is pretty interesting as to you're trying to describe or trying to build the distribution of the color of the pixels within each of the cells. So as you can imagine, if you have a really dark cell, then you are going to have maybe a pretty, I would say, you have a distribution with most of the pixels on the lower end of the numbers, as I think 0 represents black. Let me double check. I want to make sure I'm giving the, yes, as 0 represent black and 255 represent white. And I think you can see here are some pretty interesting, as you can see, the cheeks of the face have a little bit more numbers or like higher distributions on the right-hand side, whereas the pretty darker places will have more pixels or a more concentrated distribution that is actually on the lower end of the spectrum. So this gives you, I think, basically a summary statistic about how the different cells of the image might be looking like in terms of the grayscale. And then, of course, you can concatenate different features into a vector, and then you will have a summary of this. You basically transform this 2D photo into a more condensed version, like a condensed vector of 512 dimensions. Right. This is one of the feature extraction, and also this is, I think, a really straightforward technique that's not based on a lot of the more advanced filter application and kernels. Here, I'm just showing one example of the model training. As you can imagine, there's 2 images input, and they are, of course, with labels. Super important for training because, well, it's real hard to train computer vision models without labels, but I'm not saying you cannot do it, but it's just like very challenging. And you can detect the faces. And for here, you can see the feature extraction is actually extracting pretty complex features. If we're looking at here, these are just histograms about intensity of different pixels. But here you're seeing actually detecting eyebrows, noses, and mouth pieces. And you can imagine these are definitely way advanced feature extraction techniques being applied. And then all the features of fed into the convolution neural network. And we will briefly cover what that is, but it's basically a pretty complex learning system. We're going to extract more and more information over the different layers of a deep neural net. And then you can output what the final results could be. Like, I think this is still the emotion classification model here. And I think we cover in most of the machine learning or AI courses, like usually you're training a model based on optimizing one objective function, or just trying to minimize the prediction error here. So this red arrow here just illustrate this feedback loop. Like the model will start with maybe some kind of randomized initialization, or it could be an informative model, but maybe not super tuned on your training sample. But with this feedback or with this error being calculated, and our goal to minimize that, we'll be able to train the model based on the image fed into the framework. And I think the last thing I want to quickly touch on is the really hot topic. I think nowadays you cannot discuss computer vision without talking about deep neural nets, or more specifically convolution neural network, or CNN. I think I can briefly explain what convolution is. I think here there are two GIFs being shown here, and the moving 3x3 matrix on the left and the yellow colored, I would say the smaller square on the right hand side, these two are basically filters. And convolution is nothing but a simple mathematical operation that is really fundamental to a lot of the image processing operators. Convolution could be understood as this is a way to multiply the initial original image information with the filter to multiply together these two array of numbers, and then it will generate a result that can align the different dimensions of the two arrays to output a third array of numbers with the same dimensionality. I think this is really abstract as of now, but well, let me put it in maybe human words. The filter is usually designed to look for certain patterns in the image. As you are cycling through or moving this filter through the image, you're basically multiplying the smaller pieces in the image with the filters you're trying to apply. And the product of this two matrix multiplication will be the biggest when the pattern in the filter is found. And then you're basically trying to move this filter through this image and trying to summarize a lot of the information in the original raw image, and depends on the dimension of the image and the dimension of your filters you're trying to apply. This can usually achieve the goal of summarization or dimension reduction, as it is trying to convolute the raw information into the extracted feature. I know this is very abstract. I may not do a very great job summarizing what CNN is doing here, But I do have other references you can check out. If you're interested, feel free to give it a read. But for now, maybe just keep in mind it's just doing some mathematical operation of matrix multiplication, the goal of dimension reduction and feature extraction. And here is an example of CNN. It is like super cool. As we can see, these are like super nice visualization. On the top chart, you'll see this is image where you're going to take maybe a piece of that, and then it is like 28 by 28, and you're passing this filter here, which allow you to generate like I mentioned, you will have different dimensions after passing different size of filters through several times. Then you're just basically generating, you can pass different filters through the same image and to generate different, I would say this will be different feature mappings, or I forgot the terminology, but we will cover this. Basically, you will be looking for specific patterns in the image, and you will end up with different matrices representing the signals corresponding to those features. And after doing several rounds of convolution, you will end up with a nice set of features where you can just feed into a fully connected neural network just for the final task. I think shown here is we're trying to do handwritten digit classification. This is on the MNIST dataset. And I think below is a visualization about how signals are being extracted and represented throughout the stage. You can see this is a raw image here, and after the first layer of convolution, you can, different types of features might be extracted. As I think this, like I'm trying to circle here, I think this filter or this feature representation is trying to extract a horizontal line as these are being highlighted. And I think the bottom left is trying to detect a vertical edge. As I think this is not a good example, but in the 7, you can see this is really highlighted, which is pretty interesting. And then the second layer of convolution is going to extract patterns from the first convolution layer's output. So this will be aggregation or combination of everything we extract from the first layer. And then for the third layer is taking the output from the second layer, and things could be a little bit more abstract now. And then you have this dense layer taking everything, basically taking a little bit more abstract signal, and then everything will be fed into the final model, which give you the multi-class classification results. And I think I want to call back some of my initial like previous comments about building a model versus training a model, because I want to quickly touch upon the topic of transfer learning. As you can easily imagine, first of all, label data is really hard to come by. If I want to start building a model, I may not have a lot of the training sample. I need to either use someone else's data set or try to start building my own. And the latter is definitely way more difficult than the first one. And secondly, like training is actually super expensive, especially for this gigantic convolution neural nets with millions of hyperparameters. And motivated by this, we usually just use a technique of transfer learning. Transfer learning is just trying to generalize the solving one problem, trying to generalize the information or knowledge that is gained when solving one problem and try to apply it to a different but related problem. I think, for example, here, like you can see, for a lot of the image recognition problems, there are already really good convolution neural nets being pre-trained with open source, really complicated, really diverse data set. I think for here, like we could be, for example, it could be using a model that's trained on ImageNet. There are different types of objects in this data set. The model understands a lot of different object classification recognition. And so this model is already trained and fine-tuned, and you can see this is maybe the architecture of the first model. And the goal of this first model or this pre-trained model is to predict or classify based on the existing data set and existing models. And for transfer learning, we are trying to map the source or initial problem domain to our target domain. For example, I will be my goal is trying to differentiate all of these photos here or images here, which is I was thinking if you compare this target data set with the source data set, it's like actually pretty different. But a lot of the objects here are actually included in the source data set. So in this case, we know the model already understands like the context from the data source data set. We want the model to remember a lot of the knowledge it learned in achieving this first image or object classification task. And we want to keep all of these like feature extraction and feature representation layers here. And we usually call like to freeze these layers, as these are basically our feature extraction layers. And also these are this pre-trained network also preserve a lot of the information representation from this really rich training data set. And what we do here is like, we will actually remove the final dense layers. And these dense layers are basically, I think we covered before, after we got the signal like from the original image, we have usually some fully connected layers just to focus on using the extracted features as inputs to focus on the final classification or regression problem. And this is where we actually remove the older networks final dense layers, and we're going to swap in some new layers, or it doesn't necessarily need to be a neural network. For example, if we already have really good feature representation, we can also do maybe a multi-class classification. We can also do maybe some other really simple algorithms that can give you the final results we are interested in. But the goal here is let's freeze all of these convolutional layers in the middle, because these are, it's like we learn the world through already seeing so many images here. And then with all of this understanding that I trained or learned from this initial learning, I'm going to leverage all the signals I learned to achieve this final classification results. So this is what we really call transfer learning. I think it's really common in application that we will just use one of the pre-trained models and freeze the middle layers and then try to just only focus on the final layers to almost like pivot the problem and tailor it more to our own use case. And lastly, I just want to quickly touch on like, how can we use computer vision in our course? We do have a separate computer vision section in the later stage of the course, but I think Tara just mentioned she preferred we have a really quick intro to computer vision, as when you are working on the projects in smaller groups, you can think about how you can enrich your data and how you can leverage different techniques to build our own projects. So just want to maybe get computer vision in your toolbox on your radar. You know the technique is here if you ever want to use it, or just want to give you some inspiration as to what you want to build for your final project. So just want to give you maybe some really quick examples here. Like this is photo from the desserts in Meat Fresh. And there are different types of ingredients. As you can see, these are taro balls. There are also grass jelly and red beans and different types of toppings. And there's boba. Maybe we can think about how like computer vision can bring value or bring can improve the productivity of the store or improve customer experience. For example, maybe I'm just making things up here. Like maybe you can use facial recognition in the store, of course, with customer permission. Like we can recognize they are a frequent customer, or we can tie their face with their loyalty account if there is any. And then in that way, we can retrieve based on their based on their image or based on their photo, we can recognize who this person is and then retrieve their preference or historical orders. And then we can make recommendations based on this information, or we can also recommend them to try some newer products that we think is similar to things they like before. And we can also do, like, for example, automation of the dessert preparation process. Like say we can identify from the image what is the composition of the dessert. It's made of grass jelly, taro balls, boba, other toppings. And then given the menu, theoretically, a robot with robotic arms and with just some camera should be able to locate, first of all, identify what are the ingredients, second of all, locate the location of the ingredients, and then try to make the desserts automatically. And also you can have maybe a delivery robot. Once you have the desserts, you can use object tracking, like you can track who is the customer who orders this dessert and then follow them in the store and deliver the dessert to them. So I think I'm just like randomly putting together a lot of examples we covered earlier. Of course, you can think a lot of the other things. There are like infinity levels of use cases of computer vision in the broader world or in the day-to-day life around us. So I think the goal of today's lecture is just to give you like a really, really simple introduction so that you know what computer vision is capable of. And also very importantly, think about what data or what process you will need to be able to train your algorithm and also leverage computer vision to its best ability. Cool. So I think that's the end of my lecture today, and we're already like 2 minutes over in the lecture, but I do recommend this pretty short video on YouTube. I think it's like 12 minutes or something. This is super helpful. It covers a lot of the basics. For example, what is convolution? I think it might does a better job than me trying to explain it. And also how the photo works and some of the cool applications. And if you're free, just give it a quick watch. It's pretty interesting. And then a lot of the things, a lot of things I covered are linked here. If you're interested in any of the previous topics, some of these are like tutorials and some of these are lectures and sometimes blogs or papers. Feel free to give it a read, but I do highly recommend first watch this video because I think it's going to be pretty helpful to give you a better understanding. Cool, so that's it for today. And hopefully you guys have a better understanding about computer vision now compared to like 1 hour earlier. So do let me know if you have any questions. Cool, have a great weekend.